Some places in the universe are basically stuck in time. Not frozen like ice, just unchanged for billions of years, because nothing around them can push hard enough to rewrite them. Between galaxies, there are deserts of space so empty, they feel unreal. A region refuses to change when the physics still runs, but the triggers are missing. That matters because these quiet zones preserve ancient conditions like a time capsule. In crowded places, gravity makes gas collide and stars light up. Out here, matter is too spread out, so collisions almost never happen. No collisions means no heating, no shocks, and barely any chemistry. Example in real terms, intergalactic space can have just a few atoms per cubic meter. At that density, a cloud can drift for ages, barely noticing itself. Even radiation has trouble finding targets, so it cannot stir things much. Bottom line, extreme emptiness can look like no evolution for absurdly long times. One sentence recap: if nothing bumps you, you stay the same. Now zoom in on the opposite, objects so compact they become stubborn. A stable object sits in an energy sweet spot where small changes get corrected. You should care, because stability builds the long-lasting structures everything else reacts to. Gravity squeezes inward while pressure pushes outward. When those forces balance, the object stops changing fast. If the balance is strong, disturbances ring like a bell, then fade. Degeneracy pressure is the weird helper here, coming from quantum rules. Example, a white dwarf packs a sun's mass into an Earth-sized ball. It can cool for trillions of years because nothing inside easily rearranges. Even neutron stars can spin for billions of years with only slow braking. Net result, some things resist change because the forces cancel and the structure self-corrects. One sentence recap: strong internal balance makes a cosmic object stubborn. Some places stay the same because the universe keeps strict accounts. A conservation law means a total, like energy or angular momentum, cannot simply disappear. That matters because it forces every change to be paid for by another change. Spin is the one you can feel in your body. Pull your arms in and you rotate faster. In space, the same rule makes disks and orbits persist. Gas falling inward spins up, so it forms a flat disk, not a pile. Collisions can shuffle motion around, but they rarely erase the total spin. Example, protoplanetary disks survive for millions of years, long enough to build planets. Even Saturn's rings spread slowly, because angular momentum must be redistributed, not destroyed. Bottom line, conservation laws act like guardrails, limiting how fast systems can transform. One sentence recap: the universe can change shapes, but it cannot cheat the totals. Sometimes change is blocked because the road is expensive. An energy barrier is a hill you must climb before rolling down. You should care, because barriers create long-lived states, even when a lower energy state exists. Atoms do this with metastable electrons. They are not in the best state, but the jump out is unlikely. Space plasmas do it with magnetic fields that trap particles. Field lines can act like rails, guiding motion instead of mixing it. Example, in thin nebula gas, metastable oxygen can glow green for a long time. Collisions are too rare to knock it into a faster transition. Those famous aurora-like colors are delayed exits from trapped states. In bigger systems, magnetic bottles can confine hot plasma for a long time. Net result, some parts stay put because getting unstuck costs a lot up front. One sentence recap: a high barrier turns change into a slow drip. There is also frozen information, not frozen matter. The cosmic microwave background is ancient light, still filling space like a faint fog. It looks almost the same everywhere because it stopped interacting, then just coasted. That matters because it is our cleanest snapshot of the universe at about 380,000 years old. Before that time, photons kept bouncing off free electrons. Once atoms formed, the photons streamed freely through expanding space. Expansion stretches their wavelength, turning hot glow into cold microwaves. Tiny test: stir milk into coffee and patterns vanish fast. Leave dye in still water and patterns linger much longer. Example, the microwave background is about 2.7 Kelvin today. Its temperature varies by only about 1 part in 100,000 across the sky. Those tiny ripples are the seeds of future galaxies, still visible. Bottom line, when interaction turns off, information can survive for cosmic time. One sentence recap: the universe remembers when nothing touches the signal. Some things refuse to change because their clocks run absurdly slow. A timescale is the estimate for how long a process needs to matter. You should care because it tells you what is effectively permanent. Stars evolve by burning fuel, so their clock is their fusion rate. Low-mass red dwarfs sip fuel like a candle in a freezer. Their cores stay stable, and their luminosity barely creeps upward. Convection can mix their interiors, so they burn efficiently, but still slowly. Example, a red dwarf with 0.2 times the sun's mass can live around 1 trillion years. That is roughly 70 times the current age of the universe. If you meet one today, you are seeing a baby star that will outlive galaxies. Even many planets cool on timescales longer than human civilization has existed. Net result, unchanging, can simply mean we have not waited long enough. One sentence recap: slow processes look frozen on short timelines. Galaxies can look frozen, even while everything inside is moving. The trick is virial equilibrium, where random motion balances gravity on average. You should care, because it explains why clusters stay together for billions of years. Inside a cluster, galaxies orbit in all directions at around 1,000 kilometers per second. That sounds chaotic, but the overall energy budget settles into a steady balance. Gravity pulls inward, motions push outward, and the system stabilizes statistically. Mergers still happen, but they are slow, and they mostly reshuffle members. Example, the Coma cluster holds thousands of galaxies in one bound swarm. Its overall size stays similar over billions of years, even as individual galaxies swap orbits. Quick mental image, like a beehive where bees move, but the hive shape persists. Bottom line, some systems change internally, but stay the same in the big picture. One sentence recap: equilibrium can hide motion behind a steady silhouette. Now the darkest kind of stubborn: black holes that barely evaporate. A black hole is a region where gravity traps light, and the outside only reads mass, spin, and charge. That matters because it is the ultimate cosmic lockbox. Hawking radiation lets black holes lose mass, but the bigger they are, the slower it goes. The power output is tiny, like a whisper colder than deep space. For a stellar mass black hole, evaporation takes about 10 to the 67 years. That number makes the universe's age look like a rounding error. Example, Sagittarius A star is about 4 million solar masses. Its evaporation time is unimaginably longer than stars will shine. Even feeding it a little gas changes it more than Hawking radiation does. Net result, black holes do change, but on timescales that are basically irrelevant. One sentence recap: some exits exist, but they are effectively sealed. So the reason some parts refuse to change is not magic. It's emptiness, balance, conservation rules, barriers, or clocks that run too slow. The twist is that nothing happening is often physics working perfectly. You started with places stuck in time, and now you know the trick. The universe changes constantly, but it changes unevenly. If you want another deep space mystery, watch the next video on your screen.